All right, this is chapter 2, atoms and elements, and you can see the table of contents there for your lecture guide. So let's start with atoms and molecules. In Dalton's atomic theory, 1808, it had 5 basic postulates. Some of that may or may not be as true as they once thought it was, but for an ordinary chemical reaction, these things are pretty much true. Once you get into a nuclear reactor and you're splitting the atom, obviously some of these things kind of fall apart. The element is composed of extremely small, indivisible particles called atoms, right? If you're splitting the atom, that's not quite true, but for an ordinary chemical reaction, that will work. Atoms of a given element have identical properties and differ from those of different elements. Sure, we can buy that one. Atoms cannot be created nor destroyed nor transformed into atoms of other elements. For an ordinary chemical reaction, that's certainly the case. Again, what you're talking about, nuclear reactions, some of those things can be possible. Compounds are formed when atoms combine in definite whole number ratios. If I have a different whole number ratio, even though I'm talking about the same two elements, we're talking about different compounds, but the same elements in the same proportion form the same compound every time. And the relative numbers of those kinds of atoms are consistent. So an atom, as we mentioned earlier, is the smallest particle of an element that can have a stable, independent existence. If you split the atom, you don't have an atom of that element anymore. Usually there's two or more bonded together in some way, and we call that a molecule. Let's see a chemical combination of those elements. Here are some examples. You got N2, O2. Those are diatomic elements. And but they're molecules, but they're elements. S4 is a more complex element, but still considered a molecule of an element. Then you got other compounds like H2O is water, NH3 is ammonia. Those are molecules of a compound. And then we got something more complicated like C12H22O11, which is table sugar or sucrose, and that is a compound as well. So we found that the atom consists of positive, negative, and neutrally charged entities. Those are the protons, the electrons, and the neutrons. Humphrey Davy, early 1800s, found that compounds decompose into elements when you ran an electric current across it, and he concluded that those forces were electrical in nature. Michael Faraday realized that the amount of that reaction that occurs during what we call electrolysis is, or running electric current across these compounds, is proportional to the electric current passed through the compounds. We'll talk about him if you take this second course, Chem 111. So let's talk a little bit about some of these particles. A lot of chemistry talks about what the electrons are doing, and older television sets and things like that used cathode ray tubes in older electronics. A cathode ray tube consisted of 2 electrodes, sealed glass tube where you have pretty close to a vacuum or very low pressure gas in between. When a voltage is applied, you get a discharge that goes from one end of the tube to the other. And it would pass through the slit, making sure all the electrons are going the right direction, and they would travel towards the anode. And you could use that with a fluorescent screen to make sure that you're projecting a dot onto that TV, and that's how the early pictures were made. J.J. Thompson modified that experiment by adjusting the voltage and putting electrically or magnetically charged plates. Now, if you turn the cathode ray tube, we find that those electrons are negatively charged because they dip towards the positive plate and away from the negative plate. Those cathode rays ended up being called electrons. Thompson's considered the discoverer of the electrons, even though the cathode ray was known before then. He was able to measure by adjusting the magnitude of the charge on the plates. he could come up with a charge to mass ratio because you had two competing factors: inertia, which is based on the mass of the particles, and then the actual charge. And so he came up with a charge to mass ratio, but he couldn't get the charge or the mass separately. And so he came up with 1.75, etc., times 10 to the 8th coulombs per gram of electrons. Then later on, Robert A. Millikan came along and won the first Nobel Prize for an American in 1923 for his oil drop experiment. And he dropped oil drops through a plate with a hole in it, and then by hitting them with some x-rays, he was able to induce charges, and then he was able to use the charges on those plates to make them float or even rise. And then using Thompson's charge to mass ratio, he was able to determine from his experiment the charge on a single electron being 1.6 times 10 to the minus 19th coulombs. And then he did a little algebra and found that the mass of an electron was 9.1 times 10 to the negative 28 grams. I have a video of an animation of the experiment put into your course, and it'll be linked in the description of this video if you want a little bit more about that and want to see the animation in action. Eugene Goldstein had what he called canal rays. Similar to J.J. Thompson's cathode rays, they would pass from one plate to the other, but the canal rays were positive and they traveled the opposite direction. They traveled through the holes or canals that were bored into the negative electrode, which Eugene Goldstein then said there must be a positively charged particle, which ends up being called the proton. Ernest Rutherford was directing Hans Geiger and Ernst Maston's experiment in 1910. They shot alpha particles at a very thin gold foil, and then those particles were deflected to some extent. Some of them, most of them went through undeflected though, and struck the screen, and he was able to show that there was a very dense center called the nucleus of the atom. And so what he was able to determine was that the atom was mostly empty space because most of the particles pass through there undeflected. It contains a very small dense center called the nucleus, and that also nearly all the atom's mass is in the nucleus, and so the nuclear diameter ends up being 1 to 10,000 to 1 to 100,000 times the size of the atom's radius. Even if we go with the lower end of that and we say, and we give something for scale, we say that the nucleus is about the size of a tangerine, maybe 5 centimeter diameter. That means the atom would be about 3/10 of a mile in all directions. So quite a bit of a difference. And that's why only a few particles get deflected and most of them go through the empty space. Some of them may be even deflected by the way they came, depending on how close they come to the nucleus. And I also have a video of that linked into this video on YouTube, and it's linked into your coursework so that you can watch the video and you'll get a little better explanation.